Welcome to the structure analysis one. We are going to start with cantilever beam with a point load at not at the free end, but rest of the other, but near to the free end. Like uh, we can saw it in a figure number 5.6. Cantilever beam A and B with length L and put the point load at somewhere at a L1 distance at a C W kilonewton. Okay, consider a cantilever beam as we described. Okay, the beam will be bent only between A and B, but from B to C, it will remain straight since the bending moment between B and C is a zero. The portion AC of the cantilever may be taken as a similar to a cantilever in a above example. So theta C is equal to as we discussed previous lecture, same as that. So theta C is equal to W L1 square divided by 2 into EI, which is slope, and similarly YC deflection is equal to WLQ upon 3 EI. Seems portion C1B1 of the deflected beam remains straight. Slope at B will be equal to slope at C. So slope between C and B is constant. Theta B is equal to theta C is equal to WL1 square divided by 2EI. So deflection at B. YB is equal to BB1 is equal to BB2, BB1, BB2 is equal to CC1 plus B21. CC1 is equal to B21. Okay. So YC is equal to YC plus L minus L1 into theta is equal to WL1 cube divided by 3EI plus L minus L1 in bracket WL cube divided by 2EI. Now, this is the similar example in which the point load are replaced by UDL up to the same point. Okay, consider a beam A and B having a UDL W kilonewton per meter up to C or L1 length, which slope and deflection formula are taken from the cantilever beam with a full UDL, and the rest of the things are as discussed. Theta B is equal to theta C, theta C, theta C is equal to theta B because the both angle are similar. So theta C is equal to WL1 cube divided by 6 EI. So theta B is equal to S same as WL1 cube divided by 6 EI. Now for YB, deflection at that point, we can have deflection point at a C WL1 raised to 4 divided by 8 EI. But in case of YB, there is a YC plus L minus L1 into theta C. So we have the final equation is equal to WL1 raised to 4 divided by 8 EI plus L minus L1 into WL1 cube divided by 6 EI. Now there are some another examples in which cantilever partially loaded with UDL from free end. There is A, B, L1 up to C, and then after our UDL is applicable, total length is L, YB. Another example, total UDL YB1 and the upward UDL YB2. So in this case, deflection at any point may be calculated using principle of superposition. The deflection at B may be the deflection of B may be determinate as due to independent effect of the following load. First, when the whole span is loaded from A to B, when an upward UDL of W per unit run is acting on the portion AC. So theta B is equal to theta B1 minus theta B2 is equal to WL cube divided by 6EI minus WL1 cube divided by 6EI. Similarly, for YB1 minus YB2, WL raised to 4 divided by 8EI minus WL raised to L1 raised to 4 divided by 8EI plus L minus L1 into WL1 raised to cube divided by 6EI. In this case, we have both types of example solved. First, cantilever beam of total UDL applicable, and another one is cantilever beam half of the UDL is applicable. We have to find this kind of equation. So in that case, we assume all over the UDL and reduce same amount of UDL by A to C level. That's why the equation is finally we got is for these types of cantilever beam. Now cantilever beam with uniformly varying load with maximum intensity W at fixed end, as shown in figure. Consider a section XX at a distance x from the fixed end. Here fixity W kilonewton load highest, and here at B there is 0. Somewhere here the load is like this, but it, it we will calculate during the solution. Length L, somewhere X, take XX, and the rest of the distance are called L minus X because total length is X. This is a total length is L. This length is L X, and rest of the length is L minus X. Intensity of loading at X is equal to W into particular distance divided by L per unit run. That's why W into L minus X divided by L. Now for Mx is equal to minus 1/2 L minus X into W divided by L, L minus X into 1/3 L minus X. Because this is the load at this point, and the equation is 1/2 load into perpendicular distance into 1/3 of the total distance. Okay, that's why we are taking this type of equation. અહીં ગાડી બહુ બધાને ડાઉટ થતો આ ઇક્વેશન કઈ રીતે આવ્યું, તો એ ઇક્વેશન આના માટેનું ઇક્વેશન છે લોડ ઇન્ટુ પરપેન્ડિક્યુલર ડિસ્ટન્સ પણ UDL હોય તો -1/2 ઇન્ટુ પાયો ગુણ્યા વેધ. મતલબ આપણું જે વન હાફ ત્રિકોણનો રૂલ યુઝ કરવાનો. આપણો ત્રિકોણ છે એનો રૂલ એઝ્યુમ કરીએ, પણ ડાયરેક્શન ડાઉનવર્ડ એટલા માટે ફર્સ્ટ તો નેગેટિવ આવી ગયું, પછી 1/2 એ આપણો ઇક્વેશનનો છે. પાયો મતલબ L - x, પણ આપણા જોડે લોડ બી આપેલો છે આપણો જે કેલ્ક્યુલેટ કર્યો છે. તો 1/2 ગુણ્યા પાયો ગુણ્યા વેધ, એટલે આ થઈ ગયો આપણો પાયો. L - x ગુણ્યા વેધ એટલે WL ઇન્ટુ L - x, અને અપ ટુ કેટલા ડિસ્ટન્સ છે? 1/3 ઓફ L - x ડિસ્ટન્સ. એટલા માટે આ 1/3 L ઇન્ટુ x, જેના પરથી આપણે મળશે then after we got 1/6 L - x raised to 3 divided by L into W. Now integrate it. EI dy by dx is equal to W into 6L into L minus x raised to 4 divided by 4 plus C1. To simplify it, we can have the final equation as a minus W into L, minus W into in bracket L minus x the whole bracket raised to 4 divided by 24 times L plus C1. C1 is equal to constant. But we know x is equal to 0 and dy by dx is equal to 0 at the point B. That's why the only equation is C1 is equal to WL cube divided by 24. To find, so these are the our equation of. So to find deflection, we have to again integrate it. EI into y is equal to W24 by L 24 into L minus x raised to 5 divided by 5 plus WL cube divided by 24 into x plus C2. Similarly, for B point, x and y is equal to 0. That's why C2 is equal to W L raised to 4 divided by minus 120. So this is the equation of deflection. Now maximum slope and deflection occur at x is equal to x. Sorry, x is equal to x from equation 1. What are the equation 1? This. EI theta b is equal to WL cube divided by 24. Similarly, for equation 2, it is YB is equal to WL raised to 4 divided by 30 into EI. In next chapter, we are going to conduct a cantilever beam with moment at free end, and then after we are going to start our example.